Okay, so the session is being recorded. So welcome to the BA course for the September 23 term. How many of you have seen the videos of week 2? All right. So can you tell me what was the topic of discussion in week 2? Anyone? What was the topic of discussion that was happening in week 2? What was Sir talking about? And there was also 2 tutorial videos.
Probability and all.
Probability and all? Really?
To guess the fitness of the data given, right? How good was of it?
Yes, it was about probability distributions, and it was about how good my data is going to fit any theorized distribution. So you looked at empirical distributions and you had looked at standard distributions. So in today's lecture, what I would try to do is I would be talking about how this particular topic, known as the chi-square goodness of fit test, that was being performed is extended from your statistics course. So I believe in your statistics course, you would have studied about the chi-square goodness of fit test. Yes, no? Do you guys remember?
Yes, but you forgot.
You forgot? All right, fair enough. But I'll refresh it. I'll refresh it once more. And then I'll tell you how this is actually being implemented in a real kind of a business environment. Yeah, forgetting is expected. That is not a problem. But I'll tell you how it's being implemented, and then I will also talk to you about the code that was given to you and what you should do. If you had seen the tutorial videos, in Poisson distribution, I would have deliberately said an error would happen, and that you should find a solution to that error. So I'll be talking about that as well. So this is in a nutshell what we will be discussing in today's video lecture. All good? Can we get started? Yeah, all of you know awake?
Yeah.
Okay.
Yes, sir.
Super. So let's get started. Okay. Right. So in this week's content, we want to see how well a data is captured by a specific distribution. And this is important for several reasons, as Sir would have discussed. We would be seeing the statistical piece of it. What is the statistical test that we use, and how it's an extension from the basic statistical course that we saw before. So the statistical test that we are going to use is the chi-squared goodness of fit. All right. And from this point onwards, I would be referring to this as the GOF, goodness of fit. So in future lectures also, when you see me use the word GOF, I'm basically referring to what we are going to be performing. So in your statistics course, what you would have learned is that you are going to create something known as the frequency table. All right. And a frequency table is a table which will have 3 columns. The first column would be known as bins. The second is the observed frequency. And the third is the expected frequency. All right. So these are the 3 columns that you will find in a frequency table. And any table that you get in this form is known as the frequency table. So what is a bin? A bin is nothing but a range. Let's say we are considering a discrete data set where only discrete values are possible. So my first bin would have the value 1. The second is, let's say, 2. The third is 3. The fourth is 4. And the fifth is 5. For example, I have a data set where the values that I get are 1, 2, 3, 1, 4, 5, so on and so forth. And that is going to be my bin. So each distinct unique value in a discrete data set constitutes the bins. And the observed frequency is how many observations of one do I find in the data set, right? So let's say I have 5, 7, 2, 3, and let's say 8. Then these are the number of ones that I find in the data set. These are the number of 2. The 7 is the number of 2s that I find in the data set. 2 is the number of 3s that I find in the data set. 3 is the number of 4s that I find in the data set. And 8 is the number of 5s that I find in the data set. So that is the observed frequency, the observed number of times that a particular value has happened in my sample. So that is the observed frequency. Then comes the expected frequency. Let's say, since it's a discrete one, I assume it to be a Poisson distribution. So then the expected frequency is nothing but the probability mass function, which for the Poisson is going to be e power minus lambda, lambda power x by x factorial. This is the probability mass function, right? So the probability of observing a 1, where x will be equal to 1, lambda would be the mean, and x factorial. This is the probability of observing 1. This into the number of observations that I have. 5 plus 7 plus 2 plus 3 plus 8. How much is that? 7, 10, 15, 7, 10, 18, 20, 25. Right? So I have 25 values. So n is equal to 25. So I find the PMF and I multiply it by n. I get for 1. Now substitute the value of lambda, substitute the value of x, compute the PMF 2. PMF for x is equal to 2, multiply it into n. That is the expected frequency for 2. If this was indeed a Poisson distribution, let's say with a lambda of 5 and lambda of 5, then how many ones will I expect to see? How many 2s will I expect to see? How many 3s will I expect to see? How many 4s will I expect to see? How many 5s will I expect to see? Those are the expected frequencies. All right, everyone with me so far? What a frequency table is and how it's got?
Yes.
Yes.
Yeah, all right. So this is the basic frequency table. And once you have got this, then you actually perform the test where you generate a test statistic. In this case, it's going to be a chi-squared statistic. What is the formula for this chi-squared statistics? It is nothing but, let's call this O1, O2, O3, O4, O5. O1 represents the number of observed values at 1. O2 represents the number of observed values as 2, so on and so forth. Similarly, let's call these E1, E2, E3, E4, and E5. The respective expected number of values. Then my chi-squared test statistic is nothing but OI minus EI, the whole squared, by EI, summation over I is equal to 1 to 5. So that is going to be my chi-squared test statistic. So how does that look like? It's going to be O1 minus E1, the whole squared by E1, plus O2 minus E2, the whole squared by E2, plus O3 minus E3, the whole squared by E3, plus O4 minus E4, the whole squared by E4, plus O5 minus E5, the whole squared by E5. So that is going to be my chi-squared value. And the test that I'm actually performing is to see if this chi-squared value is less than or equal to my tabulated chi-squared value at a level of significance alpha and at a degrees of freedom k minus p minus 1, where K is the number of bins. P is the number of parameters. Let me put this clause that is computed. And 1 is a constant. All right. So I'm going to basically be performing a chi-square goodness of fit test on a frequency table that looks like this, such that my chi-squared value must be less than or equal to chi-squared alpha with the degrees of freedom, which is computed as k minus p minus 1. All right. Everyone with me so far? This is the basic statistics test that you will be performing.
Sir, one question I have. My
Yeah.
question is that then here the degree of freedom will be 25 minus 1 minus 1.
25?
K. What is the
No,
K
it is
number?
not. Yeah, it is not n. It is 5. It is number of bins.
Okay, okay,
It is
okay.
this, not this. This is n. This is k.
Okay. Now, in the number of bins, is it going to be a categorical variable or it is a continuous variable? How are you go for this?
I am first talking about a discrete function. So every one is a discrete value. 1, 2, 3, 4 is a discrete value, and it's always your k number of bins is always going to be discrete. It's never
Okay.
going to be a continuous value. It's always going to be a discrete, even for a continuous probability distribution like a normal, so on and so forth. I'll come to that in a minute. But
Okay.
even that, the k value will always be discrete.
Okay. Thank
It's
you.
the number of bins. It's okay.
And P here is 1 because
Yes.
only lambda is there.
Yes. P is the number of parameters that is going to be computed.
Hey, excuse me if you could hear me. I joined late. Can you please just tell me what are we doing?
We are talking about chi-square
Summarize
goodness
everything
of fit test. Chi-square goodness of fit test, and I'm first explaining what is the test that you would have studied in your statistics course, since a few people have forgotten. This is the context. Okay.
What are the number of parameters?
I'm coming to that. I'm coming to P, K, and all of that. Till this point would be your course. I will come to these numbers, what is meant by number of parameters, in a minute. Okay.
Okay, sir. Go ahead.
Right. Okay. Now comes the question. Before I come to what is K, what is P, how they are got, I'll first tell you, you have now performed the test, but you should know what hypothesis you are performing under. So the null hypothesis, H naught, is that the sample comes from the hypothesized distribution. In this case, my hypothesized distribution is going to be a Poisson distribution. Since since I took the PMF for a Poisson, this is hypothesis, null hypothesis is good, is that the sample indeed comes from the hypothesized distribution. Whereas the alternative, HA, is that it does not come from that distribution. So it's coming from a different distribution. And when once you perform this test under this null hypothesis, when you perform this test and you find that the chi-square value is less than or equal to alpha at k minus p minus 1 degrees of freedom, you conclude. What do you conclude? What is the conclusion of a hypothesis test?
It belongs to null hypothesis.
Do you
That
conclude that, or
it came or not came from the Poisson distribution?
pardon me?
That it came from the Poisson or not Poisson distribution.
Is that what you conclude from hypothesis test? What is the statistical
We
conclusion?
accept the null hypothesis here.
You accept the null hypothesis?
Or
We reject the null hypothesis.
You reject the null hypothesis?
Reject the
Both are
null
wrong.
hypothesis.
No, both are wrong. What do you conclude?
Sir,
If this condition choose, we will
Huh?
accept the hypothesis.
No. The conclusion is that we fail to accept the alternative hypothesis.
Okay, you're almost there, but you don't fail to accept the alternative hypothesis. It's always about the null hypothesis.
Yeah, we fail to
So you-
reject null hypothesis.
so
Sorry.
that you always conclude saying that you do not reject H naught. That would be the conclusion, which in turn leads to you saying that it is a Poisson. It is a Poisson. Right? So this is not the conclusion. This is the inference because of the conclusion. The conclusion is that you do not reject the null hypothesis, or you reject the null hypothesis. You never say you accept the hypothesis, null hypothesis, or accept the alternate hypothesis. The terminology is always do not reject. All right. So always remember this. Colloquially, during speaking, we might say that we accept, but that is not actually right. Whenever you are asked about hypothesis testing, the proper terminology is that you should say you do not reject the null hypothesis, or you reject the null hypothesis. That is the conclusion. Okay. So this method of concluding is actually the first technique, which is the confidence interval based technique, where you compare the chi-squared value. This is known, the one circled in red, this is known as the computed chi-squared or the computed test statistic, and the one circled in violet, this is known as the tabulated, because you will get this from a table. You will get this from a chi-squared table and as particular alpha and particular degrees of freedom. So this is known as the tabulated test statistic or tabulated chi-squared value, and this is called, the one in red circle is known as the computed test statistic or the computed chi-squared value. Based on this, if you make a conclusion, the technique that you are using is known as the confidence interval based technique. That is one way of doing it, is always possible. A second technique, which is actually more preferred by statisticians, is, there's no criteria on why it's preferred, but it is the more popular method. What is that method called? Any ideas? Because you would have heard all of this in your statistics course. So as a refresher, I'm just pulling the concept and explaining it in the context. What is the second method called? What is the value that you compute? YouTube link, I don't know.
P-value, I think.
It is the p-value technique, exactly. So this is the p-value technique. All right. The second technique that I'm now going to talk about is known as the p-value technique. So what is the p-value technique? It is nothing but the probability, the p-value that you get. The p-value is nothing but the probability of observing the sample given H naught is true. All right. So this is the probability of observing a sample, the sample that you have in hand, given that the null hypothesis is true under the criteria or conditional probability. Basically, when the null hypothesis is true, what is the probability of observing the sample? And for this, you will get some value, right? And that value is known as the p-value. And your conclusion would be based on the criteria that if the p-value is less than a level of significance, this is usually called the alpha. If the p-value is less than the level of significance, what do you conclude? What is your
Reject the
conclusion?
null hypothesis.
Sure, confident?
So I am not enough confident on the null hypothesis.
Exactly, you are right. You reject the null hypothesis. This is the I've specifically written lesser than because I wanted to explain. When the p-value is less than the level of significance, you reject H naught. Else, if it is greater than or equal to alpha, you do not reject H naught. So this would be the criteria in the p-value technique. All right, you guys understood the difference between the two techniques that you have, and how do you make a conclusion? You make a conclusion of whether rejecting or do not rejecting the null hypothesis. All this point that I've discussed so far is the statistics piece of it. Any questions?
So very well explained, sir.
Huh?
Very well explained.
Oh, thank you. So any other doubts in this piece from anyone?
Yeah, the guessing the distribution, whether it's Poisson, is it a random guess or like a visual plot? We guess the initial
Wonderful. I'm going to come to that in the business piece of it. That is going to be the exact discussion for the rest of this session.
Yeah.
Right? That is going to be exact discussion. How would you arrive at that frequency table? That is the question. That is what we are going to discuss after this point. All right. Okay. So this, like I said, please stream these sessions on YouTube too, or please update. Oh, it is being streamed. You see that I don't know whether you are able to see the screen. Let me just show it to you. Entire screen. You see, it is being streamed. The call is being streamed. So you should have that YouTube link with you. It's not available. Copy stream. See if you get it in this link. I do not know. All right. Anyhow, the operational issue, but you will be given the recorded session. The session is also being recorded. You will get it afterwards. But let me try to see what happens on this on the back end. Anyhow, so all of this that you are doing is the statistical piece based on which you will conclude whether your hypothesis is correct or not. Now comes two interesting questions. All right. The first one that was raised is, what is this k minus p minus 1? Correct. So the DOF, why is it k minus p minus 1? That is the first question, because usually in your statistical courses, this DOF would have been called as k minus 1. They would not have given you this p. Why does that p come in? That is the first question. And the second question that is there is how to construct a frequency table for a business problem. Right? These are the two questions that arise. In fact, you can call this as question 2 and call this as question 1 also, because we'll answer this first. Once I answer this frequency table construction, automatically the question of why the P comes in will be answered. So question 1 could actually be how to construct the frequency table, and then why in that frequency table you are having a P variable coming in your decision of in your degrees of freedom. All right. So that is going to be the rest of the discussion for the remaining 30 minutes of our live session today. Having said that, let's now look at a business problem that we have.
Sir, excuse me.
Yes.
Can you please tell me what are degrees of freedom in a statistical context?
Okay. Degrees of freedom, more than a statistical context, I'll give you the intuition behind it. The degrees of freedom basically represent the different directions in which I am allowed to move given a certain space, right? So let's say you are put in a room and you have walls and you are put in a space and you have walls on 3 sides. Then your degree of freedom is only 1. You can either move only in the direction where there is no wall, right? Similarly, your models that you build have a capability to move in a space which get constrained, which has the number of directions in which it can move is basically given by the degrees of freedom. Okay, making sense?
Sir, I know the physics part of it. Like you explained, like if I'm in the room and 3 walls are there, I can move. Like I'm not able to connect it with the models.
you're not able to connect it with the models. Okay. Let's look at it in this context. For example, I have 5 bins. All right, I will tell this to you now, but you will understand better once I explain how to construct a frequency table. That will make more sense. I have 5 bins. And do I have, when I put O1 minus E1 by E1, O1 minus E1 the whole square in my formula, when I put O1 minus E1 the whole square by E1 and compute this chi-squared statistics, how much movement in this chi-squared statistics do I permit? That is captured by this degrees of freedom. At the degrees of freedom, as I increase the degrees of freedom, the value of chi-squared alpha k minus p minus 1 will increase, which means I will be giving my computed test statistic more space to expand, more variability. So my O1 and E1 can be more larger. O1 minus E1, that space can become more larger. But when I put up k minus p minus 1, which is small, the value of this chi-squared tabulated value will come down, which means my computed value should also be small if I do not want to check the null. Making sense now?
Yes. Thank you.
All right, so that is the context. That is the movement that is permitted. Okay. All right.
So, sir, if the degree of freedom increased, then the chi-square value is also increased?
This chi-square tabulated value increases, which means
Okay.
the range of possible values for your chi-square increases. Correct?
So, in other words, I can say if the number of beans is increased, here it is 5. So, if it become 10, then obviously chi-square value increased.
This will also increase, this will also increase. No? Or this could decrease, this could also decrease. That all depends on your P and your chi-squared value. Because the more you have to do more OI minus EI computations, right? So obviously they get adjusted.
Okay, sir.
Right? Okay. All right. Any other questions till now? All right. So let's say now I am giving you a data set which is having some numbers. Let's say for the sake of explanation, let's take a discrete data set, which is the number of defective items I produce in every shift of my production. So that could be any value between, let's say, 1 to 10. I produce 10 cars in my production. So I can have a value between 1 to 10 as my number of defects. Or in fact, this can be, 1 to 10 as my number of defects. So I can have one defect. Let's make it a smaller number so that my table becomes small. So it can be any number between 1 to 3. I make a batch of cars. In that, I can have a number of defects can be between 1 to 3. I can have 1 defect, 2 defects, or 3 defects. So what I do, I produce, let's say, 100 cars. Or this could be the number of defects per car. Let's put it like that. Number of defects in a car that I produce. All right. So that is going to be between 1 to 3. Now I produce 100 cars. All right. I produce 100 cars. In that 100, I find a sample that looks like 1, 1, 1. Let's say 1 is coming 10 times. Then 2 is coming 20 times. Then 3 is coming 30 times, for example. All right. So what happens? 30 plus 20 plus 10, that is 60. So I have found that 60 cars have defect, and in that 10 cars have 1 defect, 20 cars have 2 defects, and 30 cars have 3 defects. What happened to the remaining 40 cars? I've taken a sample of 100 cars, out of which 60 are having some form of defects. Then what is the remaining 40?
0 defect.
Exactly. So there is a 0 defect segment that I must consider. 1 to 3 defects are what I see, but there is also a 0 category that I have to consider. So this is the first business instance. Given a sample, you should always know the sample size, what are the values that you get and whether the values that you get are matching your sample size. If not, you should appropriately adjust with a logical number. Okay? Got it? Everyone clear so far?
Yes. Yeah.
Sir, we are producing 3 parts in a car.
No, I'm telling a car can have 3 defects. Maximum 3 defects.
Okay, sir.
All right? I produce a car, it can have maximum 3 defects. It can have an engine defect, let's say a clutch defect, transmission defect. Maximum 3 defects. There are no other defects that are possible. So you could either have only the engine defect or the engine and transmission or this thing, any combination of those 3. Right? But then it's called a number of times that is number of cars with 1 defect, number of cars with 2 defects, number of cars with 3 defects. Okay? Everyone clear so far?
Yes. Yeah.
This is the data set that is given to you. With this, now you must say what type of a distribution that the number of defects that I see in a car follow. That is the question. How would you identify that? That you identify using first descriptive statistics. You try to see what is the mean, what is the variance, so on and so forth. Then you go to the next level of once you have got the descriptive statistics, you then build your visuals, your PP plot, QQ plot, narrowed it down to a set of possible distributions, and then you build the frequency table. Okay? I'm not going to discuss the descriptive statistics and the visualization piece that you see in the tutorial. My focus is once you have got this list, you have to convert it to a frequency table, right? How do you do that? So you basically do that by considering the 3 columns, constructing the 3 columns, which are going to be bins, observed frequency, and the expected frequency. What are the possible bins? That is nothing than the possible values from my data set. And that includes the 0, 1, 2, and 3. What is the observed frequency? Number of times a particular 0 has happened. So 0 has happened 40 times, 1 has happened 10 times, 2 has happened 20 times, and 3 has happened 30 times. That is your observed frequency. Now comes the question of what is my lambda? Or let's say what is my mean? Usually when we use discrete statistics with defects, it's usually a Poisson, right? So you'll have to compute the lambda. So what is the value of lambda?
It is
What is the lambda?
1 by average.
Average of what? I have 2 columns. I have 0, 1, 2,
0
3. I
into
have
40, 1 into 10, plus 2 into 20, plus 3 into 30.
Wonderful. By divided by
All the values.
by all the values of 0, 1, 2, 3 or 40, 10, 10, 20, 30.
40, 10, 20, 30, I believe.
Exactly. So 0 into 40 plus 1 into 10 plus 2 into 20 plus 3 into 30 divided by 30 plus 20, 50, 50, 60, 100. The sample size. This gives you your lambda. Mean of a Poisson distribution. All right. Everyone clear?
Yes.
So why
Yes, sir.
Poisson?
Poisson, like I said, usually for defect distributions, Poisson would be the best fit. Usually, generally. So I'm just taking as a Poisson here. But you have to use a narrowing method. You will have to use the descriptive statistics.
Distribution.
Pardon me?
Can we do this question with another distribution, like if we take another distribution? Yeah.
Okay, let me do one thing. Let me do a uniform. But it's a uniform is a continuous distribution. Uniform normal is a continuous, Poisson discrete, binorm. I don't think you guys will know any other discrete distribution in this course. That is why I'm taking a Poisson distribution. All right. Okay. Anyhow, next I'll talk about a continuous distribution. There, all of these will get resolved. I'll talk about uniform. There it will get resolved.
Yeah.
Okay. Right. So this is for a Poisson. Okay, got it? So now we have got the lambda. You can compute the expected frequencies for each of these. Let's call them E1, E2, E3, and E4. That is not, that is actually not in scope for us because I'm not in a statistics course where you compute these. This you will do in a tool. Look at the tutorial, you will get it. So this is how you compute the frequency table. Here comes the catch. The error that will pop up in most cases when you do this is that there is a mismatch between 100 here and some of EIs that happen over here. Oh, sorry, not EI squared. The sum of expected frequency E1 plus E2 plus E3 plus E4. This sum will not be equal to 100. All right. In that case, what should you do? That is the question that is posed in your video. So what should you do in that case?
We can give the remaining options to the last point.
Why the last point? It is wrong. That is why this time, last time I had a different question. This time I'm changing the question. What is the logic? You're right. Your approach is right, but adding it to the last is wrong. That talks in the video.
Divide it
Here
and,
and
to all of them.
You will divide it to all of them. That is a fix.
Yeah, I mean-
Wonderful. So there is a fix and there is a correct solution. If let's say the difference between 100 and this is let's say 4, for example, and I have 4 bins, I could do +1, +1, +1, +1, and the solution is gone. Solution, and I can proceed. I will overcome the error. Most probably your solution will be in a range, not a problem. Will be in the range that we provide. But this is only a fix. It is not the correct method. What is the correct solution? Why is this happening and what is the correct solution? Abhinath told me it is right. You should add it to the last, but you should add it, but adding to the last is wrong in this problem. Where should you add it? And how that addition comes? What is the logic behind that addition?
Adding it to the least observed frequency.
Adding to the least observed frequency? No, that is also not correct.
Isn't that the graph doesn't end at certain point? It will be, we won't finish it. It will be keep going on, right, in that direction. Does it imply
That is okay. That will be correct when I said when you put this as 3 plus. When you put this as 3 or more defects, that is correct.
Okay.
Right? That is correct. You're still okay. 3 or more. You can add it. Like I said, like Abhinath said, I can add it to the E4. When I give only 3, you cannot add it. But when I say 3 or more, then his logic applies. So the correct method to actually write the bins then would be, if the solution that I'm going to propose is going to be to add it to the last bin, then I should say something like this: 0, 1, 2, or 3 or more, and proceed. Else what I should do is 3, 2, 1, or 0 or nothing. That is the solution that I should take, because I have specified that there can be maximum of only 3 defects. Then the number of units that I'm not matching should go into the 0 category. It cannot go into the 3 category. Got it?
Can you repeat that? I'm not getting it.
Here I have specified that the number of defects that I can see is maximum only 3. That was the problem with which I started.
Yeah.
I cannot have more than 3. So it would not be logical to add these extra values to the third bucket, because if I want to add it to the third bucket, I must put it as 3 plus, which is wrong in the business context, because the business says I cannot have more than 3 this thing. Then the only logical place to have it is 0 or less than 0. I produce extremely pristine products, there I add it. Right? So for this particular problem, the difference that I get should be added to the 0th bucket and not to the third bucket. I will have more observations in 0, but I cannot have 3 or more probability. Okay? Making sense?
Sir, I don't get it that why that expected frequency will not be matched with observed one.
Wonderful question. I'll answer that. That is in fact the logic of that plan. How you basically do this is, how are you computing the expected frequency? Can you tell me that? What is the formula for EI?
So it will be n into PMF.
N into PMF. And what is the formula for PMF? E power minus lambda, lambda power xi by xi factorial. This is the formula. This number is going to be a decimal. Correct? And obviously you are going to do some rounding off.
Okay.
Which means what will happen? The PMF for 1. Now PMF for 0, PMF for 1, PMF of 2, and the PMF of 3, when you add all of these, they will not add up to 1. They will be a number less than 1. Because of some round off errors that may pop up.
Okay.
Correct? Since they are less than 1, obviously these will not add up to the entire n. Which means you must make sure that at least one of these, so to make them add up to 1, what you usually do is, you use for this problem, since you have only a maximum of 3 possible defects, you will compute for PMF1, PMF2, PMF3, and then for PMF0, you will put 1 minus all of these is equal to PMF3. PMF0, sorry, PMF0.
Okay, sir. So my question is that suppose I got a sample where I only can observe 1, 2, 3, not 0, and then I got this error. Then how I solve it?
That is what I'm trying to say. How you solve it is you got a sample where you have only 1, 2, and 3,
and that is business thing.
And let's say you don't have n also. N is also not told. Okay, n is also not told to you. Then what you take? You take n as a sample size. You count the number of 1s, number of 2s, number of 3s. In our case, it's going to be 10 plus 20 plus 30, which is 60. Okay? You solve this problem. Again, you will end up with the same thing, that this is less than 1. Then you make an assumption saying that the sample has only observations up to 3. I will put 3 plus and add the value to the last bucket.
Okay.
That is an assumption that you make. Okay. You can also make a inverse assumption saying that I would have a bucket with 0, 1, 2, 3 and compute this value, and whatever is the difference, put it in 0. That is also fine. That is an assumption. Right? For the business problem, to solve it, you assume. You never make this assumption usually, because you assume that the sample is coming. So you take 3 plus.
Okay.
Okay, you take 3 plus, and that is where you add the remaining values to 3.
So, sir, one out of turn question. So, lot of time when we do the ChiSquare distribution in Python, we found this type of error. So, is it because of this they are not able to? If there is a big data set, then there is a gap is happening.
Exactly. This is why the error. This is why I don't know what error it's called.
There is a very nasty error they throw.
No. It comes only when you perform the ChiSquare test.
Yes.
Yeah. Yes. That error comes. It's not very nasty. It's a logical error. It will not come in older versions of your Python code. But in latest versions of Python code, this has been incorporated because your expected frequency, mismatch between observed and expected frequency, that is the error that will pop up.
Okay.
Right?
Thanks. It is a long problem for me. I don't understand that.
And it can be solved by doing this. You take PMF1, PMF2, and you for the last bucket, you take 1 minus PMF1 minus PMF2. If you do this, you will get it. And this is the logical reason. Because the sum of probabilities of all the buckets should add up to 1. Because ultimately the chi-square distribution is a distribution between that is going to have a probability sequence of 1. Correct? Everyone got it?
Yes.
But we can only do this if this is 3 plus, right?
You generally do it if it's 3 plus. For my business problem here, I have told you that it is only 3, and I have told you the sample size is 100, so you must add it to 0. You cannot create a new expected frequency of 3 plus. So you must create 0 minus.
You will calculate PMF1, PMF2, PMF3, subtract 1 from it, 1 from the sum of this, and put it in 0, right?
And put it in 0, yes.
Okay.
So based on your business context, based on the problem context, you should see where to add it, either in 0 or in 3. Okay? Well and good. So this is how you perform your chi-squared test for your business problem. So you should construct the frequency table for the business problem that is given, and when you are constructing that, you should make sure that the expected values and the observed values sum up to the n that you have. Okay, so the n can either be the sum of observed values if I have not specified the sample size. If I have specified the sample size, appropriately add bins that is required for you. All of you clear? Yes, no? Okay. Once that is clear, now comes the question of why k minus p minus 1, the degrees of freedom. Why do I have to reduce this p? For your business problem, how did you compute your expected frequency? You computed using n into PMF. And how was the PMF computed? It was computed based on the lambda that you got from the sample. You had a sample, and from that sample, you computed a lambda and used that to compute the expected frequency. Since you use...
So we're calculating based on the observed frequency distribution.
Yeah, you are calculating based on your sample. The observed frequency comes from your sample.
Right.
Since you are computing one parameter, which is the only parameter required for a Poisson from the sample, you will have to reduce those many degrees of freedom in your model. So if I had 4 bins, and if I computed lambda 1 minus 1, that is going to be 2 is going to be your degrees of freedom.
Sir, can you please repeat that once more?
This P is the number of parameters that you compute from the sample for getting the expected frequency. For a Poisson distribution, that number is going to be a lambda which is got from the sample here. So you will do k minus p minus 1. If you, in your original statistics course, you are given an observed frequency and given an expected frequency. You never compute your lambda from a sample. So in that case, your degrees of freedom was k minus 1. Whereas in your business problem, since you are constructing the frequency table from scratch, and when you are constructing this table, you will need to know the probability mass function or the probability density function if it's a continuous distribution. You need to compute that. To compute that, you need to know the parameters of the distribution. And the parameters of the distribution are got from the sample. In this case, it is the lambda. Since you are talking about a Poisson, you need the lambda. So the lambda is taken and computed from the sample. So you will have to lose so many degrees of freedom. So it is k minus p minus 1. Making sense?
Yes. So, sir, I have one question. So that means if I choose a distribution, that distribution have a 3-4 parameters, then my bin size should be in certain above certain limit.
Not
I give you. Yeah. So
okay,
then it will be negative. Suppose for a
okay, k cannot be negative. So the minimum value is there. Usually there are not more than 3 parameters distributions. And for our course, we are looking at only 3 distributions. One is the Poisson, for which you need the lambda. The second is the normal, for which you need the mu and sigma squared. And the third is the uniform, for which you need the minimum and maximum value A and B.
Yeah, sir, I agree. I agree with you. Just I am asking the question that suppose I have a distribution of 3 parameters or 2 parameters, and I have a 2 bins. Then
you cannot have 2 bins.
I cannot have two bins then.
You cannot have two bins.
Yes. Then it will be negative.
Yeah, obviously. There is no possibility for negative degrees of freedom.
And 0 degree of freedom is allowed?
Usually they will not go for it. You will not even find tables with 0 degrees of freedom. You need at least one.
Okay.
At least one. So your K should at least be greater than P plus 1.
Okay.
Sir, could you
P
mention
plus 2, P
third
plus P plus 2.
distribution?
Can I? Uniform.
What is the third distribution?
This is
it's
a uniform.
Okay. It's uniform.
This is a uniform. This is a normal.
So most business problems would fall within one of these three distributions?
Yeah. Usually in the real world business problems, you might have to build empirical distributions. That is why Sir talks about them. But for our course level, since it's a beginning level course, we talk about only these three: Poisson, normal, and uniform.
Okay.
This is a discrete. These two are continuous. All right. These two are continuous distributions. This is a discrete distribution. All right. So when I build a model with a Poisson, my P, okay, I should have, okay. So when I build a model with my Poisson, my P is equal to 1. When I build a chi-squared GOF with a Poisson, my P is equal to 1. When I build a chi-squared GOF with a normal, oh, what happened? Yeah. My P is equal to 2. When I build a chi-squared distribution with a uniform, my P is equal to 3. Now here comes the most important trick, important catch. All of this is okay when I am building this frequency table from using a lambda computed from the sample. Let's say I specify in my business problem that the number of defects in a car that I can produce is between 1 to 3, and it follows a Poisson with lambda of, let's say, 2.5. For example, I specify that. Then your degrees of freedom is not K minus P minus 1. It is just K minus 1 because you are building your E expected frequencies using a given lambda. You are not computing it from the sample. All right. Got it?
Yes, sir. But if my mean is 2.5, then what I will do?
If your mean is 2.5, you will still apply the
Oh,
same
okay.
thing.
Got it.
Instead of using the lambda computed, you are giving a lambda. That is
yes, sir. Bad question, sir. So if the lambda is given, then I should not go for an do not consider it for degree of freedom, correct?
You should not consider the minus. Yes, you should not consider the minus P in your degrees of freedom. Okay. Now comes the interesting observation of why all of this in your p-value, why people prefer the p-value. The p-value is the probability of observing the sample when H0 is true. That is the criteria, right? Why is that? Because you are doing all of these computations considering that this originally follows a distribution where the lambda is specified. You are computing the EIs for a lambda that you are assuming the distribution to come from. And you assume that the sample is coming from that. Then what is the probability? That is why the p-value in your statistics course is probability of observing the sample given the null hypothesis is true. The null hypothesis that this indeed is coming from a Poisson distribution which has a lambda of 2.5 or which has a lambda as specified in the sample. So on and so forth. That is the wrap up. Yeah.
I have a question. Could you go back to this part where the level of significance part? The p-value.
One second. Yes.
Here we are saying P is the probability of observing the sample given that null hypothesis is true. Generally, you would expect what the P to be something like 0.95, 0.80, something like that, right?
It depends. I I will not expect the p-value to be something. I will expect the p-value
No,
to
no,
be
I'm
less
just
than
saying,
alpha.
for example, it could be 0.8, 0.95, something like that, right?
It could be 0.03. Anything can be there.
Yeah,
I
it
would,
can be.
it can be. I would usually, that is what I would usually expect a point p-value that is lesser than my greater than my alpha to not reject it, lesser than my alpha to reject it.
I'm a little confused because I know about confidence intervals and level of significance is usually 1 minus that, right?
Level of significance. No, alpha is the level of significance. That is
Yeah.
level
So,
of
for
confidence is
example, if
1 minus
level of
alpha.
significance is 5%,
5% is 0.05.
yeah. And so, what is
The
the P?
p-value. The p-value must be less than 0.05. The confidence interval will be a 95% confidence interval.
Yes, yes. So, if
That is
I.
so 95% confidence interval corresponds to a level of significance of 5%, and vice
Yes,
versa.
yes, yes.
The alpha is 5%.
So,
So,
aren't we saying in a way that this, with this, the probability of observing the sample, given that the null hypothesis is true, is sort of like a confidence that we're confident, say 95%, that it will
not at
be
all.
actually.
No. The interpretation for confidence interval is completely different. The interpretation of alpha is completely different. Confidence interval basically tells you if you take a large number of samples, then the capability of the confidence interval to capture the true value is 95%. I'm not going to get into the statistical discussion, but that is the confidence interval. 95% confidence interval is basically that. If I build, let's say, 100 confidence intervals, then 95% of them will capture the true value of my parameter. That is the confidence interval.
So, here, if P was 0.02, we would then reject the
You
null
will reject
hypothesis.
the null hypothesis. The p-value is pure probability,
Okay.
right?
Yeah.
So could you please repeat the confidence interval part?
Like I said, I'm not going to go into that statistical discussion, but generally this is the interpretation. Let's say I build 100 confidence intervals of 95%. All right, I built 95% confidence interval. Then 95 of those confidence interval will have the true value inside them. That is the interpretation of 95% confidence interval, right? Like I said, you should revisit your statistical course where they talk about confidence interval to understand that that is not in scope for us. My thing is, given some values, whether you reject the null or do not reject the null. That is going to be my discussion and how you build towards that. Okay.
Yes, sir.
So the two things are completely different. Here, most of my questions will be revolving around p-value because that is where most of you make mistakes. So that is where I like to ask questions. So always remember p-value, probability of observing the sample given H naught is true, and it must be less than the level of significance to reject it. Okay. So this was what I wanted to discuss in a nutshell. You can extend the same thing to a uniform distribution, the same thing to a normal distribution. All right. Our TA, Kalpita, are you there in the call today? I do not know.
Yes, sir. Good evening.
Oh, good evening. All right. So I will give her the responsibility of solving some practice problems during her tutorial sessions this week. She will schedule it and send you the calendar invite. So during that, she might solve a few practice problems where you will look at uniform distribution. Please do that, Kalpita. All right.
Yeah, sure, sir.
Done. So any other questions on this concept? This is the primary concept in week 2. So any questions? Do you have any doubts here? When are the tutorial sessions? Yeah. tutorial sessions, Kalpita will find a time and she will share it with you guys. Okay, you will get an announcement.
So I would like to tell you all that I do not have the access of the course calendar yet. As soon as I have it, I'll schedule a session and share it with you all. Is that okay?
Is this the first live session of business analytics?
Yes, this is the first live session. We generally don't have one for week 1, primarily because it's about visualization. We believe that you can catch on to it. Week 2 is where a bit of these tricky concepts starts coming in.
Is there any YouTube channel where you guys upload this? If there is, please share the link.
Yes, we do have the YouTube channel Business Analytics. Let me just try to open it. Show you. This is the channel. They might rename it to May 2020, September 2023. We'll get that to you. This is the channel, and all the links will be available. Yeah. I'll ask them to send out an announcement once they have created the channel. September 2022, maybe the playlist. Once the first live session goes live, it will get added. And you will be having it in your, most probably they'll also add it to your calendar. I'll ask them to do it. Yeah. Okay. So any other questions?
Will that collab notebook which was done in the session, recorded session that we shared with us?
Yeah, good. It is there. It is already there. You will have got access to it. Just check the additional contents page. Maybe in supplementary week 2 it must be there. Thank you for reminding me. I forgot to tell. There was a small error in the code. In the video, we have added a note. Please read the note. The code should actually be, I forgot the exact thing. It should be observed. I don't remember the first piece, but it should be observed frequency, expected frequency, and there is a delta degrees of freedom, DDOF, which must be equal to the number of parameters that you compute. The code would be this line. All right. So just check. It's chi-squared, I believe. Something, chi-squared something. Observed frequency, expected frequency. This piece would be missing. So just make sure that you add it. This basically refers to the K minus P minus 1. This P is basically is referred to by the DDOF in your code. This is missing in the code that we have shared and also the tutorial video that we have done. So make sure that you add this when you solve the assignment problems and when you solve the problem also. Okay. Yeah, thank you for reminding me. I forgot to mention this. It is put as a note in the tutorial video that is there. So when you see the tutorial video, at the appropriate time where this code is being displayed, you will get a note below the screen. So make sure that you read the note. Yeah.
It's for both the distributions, right?
It's for both tutorials, any tutorial.
Okay.
It's for any distribution. Whenever the default value, if you don't specify the DDOF, the default value is 0.
Okay.
So you must specify it for your context appropriately. If it's a normal, it's 2. If it's a uniform, it's 2. If it's a Poisson, it's 1. Exponential, so on and so forth. Appropriately, you should specify. Okay. So any other queries?
So, can you go for a PP curve and QQ curve? I'm not able to differentiate. What is the exact difference between these two?
Okay. What I'll do is I'll discuss that next session, week 3. Now we have already overshot time, but I'll give you a gist.
Okay.
In a probability, in a QQ plot, in a quantile plot, you are basically checking how good the values in a quantile are matching. Quantile is basically your 25th quartile, median, 75 percentile, so on and so forth. So between any given quantile, how good is your theoretical value and your actual value matching. That is a quantile plot. Whereas in a probability plot, you're basically checking the PMF versus PMF or the PDF versus the PDF. Right? So how good are those two matching? And appropriately you make inferences.
Okay. So is there will be any second session on the week 2?
There is no second session on week 2. I would maybe briefly talk about this in week 3 when I do my week 3 session. If you want, I have a scapegoat this time, who is Kalpita. So if you want, maybe Kalpita can explain. If she finds it difficult, she can ask me and I'll also explain to her and she can explain. Or we can always do one more session.
And sir,
Alright.
can you briefly describe what is the skewness and kurtosis that actually I am a bit confused.
Okay.
Sorry.
Okay. Yeah, because we just introduce you to certain terms, but we don't expect you to be in detail for this course. I will extend skewness, not kurtosis. Skewness is basically referring to whether my distribution, whether my values are lying towards one end or the other. Okay. So the easiest way to explain skewness would be like this. All right. So in this kind of a distribution, what has happened is all my values are sitting on this side of my curve. This is a right skew.
No, sir, this is a left skew, no?
No, I think the professor, that's what I was about to ask. I think he made a mistake. He told this as a left skew.
It is skewed on the left, no?
No, but this is on the, it's a confusion there. Can you explain it?
Yeah.
This is
It is left skewed.
Left skewed.
What am I doing? I'm half sleeping. Wait.
It's left
Net
skewed
right
because the
skewed.
tail is longer in the left.
But in the net, depends on the bell portion, we say left or right. In the internet, it is like this is right skewed, but in the lecture, it is
This should be right skewed. If my no, the tail is
Even
on the
I
left.
understood, but the professor is telling different, so that's why it is a.
Okay, let me check the video. Let me check the video and also confirm. My remembrance is this is right, tail is on the left.
Even I got confused because in the
This is
lecture.
my remembrance. That is why I immediately do. All right, let me do one thing. Let me take skewness next week. All right, I will also do a check on the videos because I will also have to check the videos. I'll check the videos and I'll also check the check my notes, my books, and then I'll come back to you. My remembrance is this because data is skewed towards the right and the tail is on the left. That is how I usually remember my
But
concept.
professors say it in different way. Actually, it is
Let me check. Let me check. It might be a spot of a moment error that might have happened in the video. Let me just check. If it's there, you can always correct it. I will check. Okay. Right. So I'll check and come. Once professor has said something and you guys are confident that professor has said something, I will check and come. Okay. Right. I will do that. I will also check. You can also post this in the Discord. I'll also answer it there.
Okay.
Okay. Anything else?
So one more session on the skew, kurtosis, and other things. It is really helpful session.
Like I said, kurtosis is going to be out of scope. We generally do not talk much about kurtosis. Skewness, PPQQ, maybe I will see if I can. All right. Or I'll obviously add it in the next week. Next week live session, I'll add it and we'll discuss. Not an issue.
So the graded start from week 3, is that?
Your first, for this course, there is no weekly graded assignments. You will have 3 assignments in total. The first assignment will be launched at week 4, I believe. Yeah. Timelines, just check week 4, then week 8, week 4, week 7. All right, I will have to check that. Week 3, yeah. Week 3, week 7, and then week 9. I believe that is the timeline. I do not know if there is any change, but yeah, week 1 and week 1, 2, 3 is 1. Then 4, 5, 6 is 1. Then 7, I believe. 7, 8, 9.
Okay.
That is a grouping, I believe. I don't remember. So I'll have to check the grading document.
And there will be quizzes as usual. Quizzes will be there.
You will have quiz 1, quiz 2, and the EDTOP. Two quizzes in center at TCS Ion. 3 graded assignments and 1 EDTOP. And it is mandatory that you take at least one of the first two assignments, assignment 1 or assignment 2. It is mandatory that you should take at least one of them to be eligible for the EDTOP. If you miss both assignment 1 and assignment 2, you will not be eligible for the EDTOP.
Oh. Okay.
All right.
So I request that TA session should be recorded because maybe this time I am not able to attend, but in office I cannot able to attend this TA session.
Usually we keep the sessions in the evening only.
But
Last time it was like that.
so but
TA
for working
sessions
professional, a lot of
and-
late night call is there. I mean,
and then
a lot of
TA
evening.
TA sessions we usually do not record them, because we don't want to put that stress on the TA. That is the reason that we don't record. But if the TA is okay, and if I have to also talk to my admin people, operations people, if they are also okay, then we can record. I'll get back to you on that.
Okay.
TA session will be updated in the calendar, right? As of now, I am not seeing
Yes. Kalpina has not got access to the calendar.
Okay.
Once she gets
She's-
access,
okay.
and once she gets access, we will add it to the calendar and it will be coming. Same way, the YouTube link should also get uploaded to our YouTube channel. Hopefully, it will get done. Last time we faced some issues towards the end. Hope it's resolved this time. So we'll get it done. And these recorded sessions of the instructed sessions will be recorded and will be shared on your YouTube.
Sir, can you share this whiteboard slides, sir?
Whiteboard we don't share, man. It is you are getting the recorded video session from there only. You can take it now. Because this whiteboard is not is my personal space, so I do not share personal space.
Okay, sir. Maybe I thought like view only.
I generally do not do that in my personal space because then a lot of people get access and I cannot keep track.
Okay, sir. Sir, otherwise zoom out, sir. I will take screenshot.
Yeah, you will get a video, man, and then you will have everything now.
Otherwise, I need to go through the video again, and that's it.
You need to.
If you are able to understand without going to the video, then fine, fair enough.
Thank you, sir. Good night.
All right. Thank you. Good night.
And night.
Thank you, sir.
Okay, thank you, guys. So there are no more questions. We have 17 people. If it becomes less than 5, then I'll also log off. I will stop recording the session now.